Hello everyone. This week we shall continue to study combinatories and introduce to everyone some delightful sequences. So some people might say, but we've already covered the Fibonacci sequence, right? Indeed, if we see that Fibonacci sequence holds the secret laws of the natural world, then we shall introduce a sequence often known as a wizard in computer science. What is it called? Its name is a Catalan number. Why do we say the Catalan number is a wizard in computer science? Let's take an example. Many people know that in computer science there is a widely used data structure known as a stack. What does a stack look like? It's like a storage section. But for this storage space, entry and exit is limited to the top. So when objects are pushed in or popped out, this must take place at the top. With this rule in mind, we have to consider a problem. If I have an infinitely large stack, its pushing order is predetermined, that is from 1 to m. Then how many popping orders are there? For this problem, let's take a relatively simple example. Say if we have only 4 elements, 1, 2, 3, 4, they enter and exit the stack in order. So how many different orders there? Let's continue the previous example. For the numbers 1, 2, 3, 4, 1 is pushed in first, so that is at the bottom of the stack. Then 2 enters the stack, but now we have to use 2, so that 2 has to be popped out first. 1 has to be used next, so 1 also has to leave the stack. Now we find that in fact we already have part of the popping sequences. 2 leave first, followed by 1. Let's see, 3 enter the stacks next and has to be used immediately. Then 3 has to leave the stack. Of course, we can also have 4 entering and then leaving. Now we have given example tells everyone that for the 4 elements 1, 2, 3, 4, this is a possible popping sequence 2, 1, 3, 4. In different cases, how many different popping sequences are generated? Let's analyze it. In fact, we can see if we want to use the recurrence relation to express this, can we convert the stack pop problem to several smaller problems? Let's follow this line of thought. Would it be possible to separate into the individual steps when the stack was first empty, enabling the stepwise calculation? If we take the previous case, we see that after 1 enters the stack, 2 enters afterward, then 2 leaves, then 1 leaves. Now, there are no elements left in the stack. It is the first time the stack is empty if we exclude the very beginning. So, if we take this to be the time of division, then we find that in fact, we have now converted the stack pop problem into 2 stack pop problem. Part of this problem is 1 and 2 enter and then exit. So, only 3 and 4 remain to enter and exit. And now we have divided the original stack pop problem into 2 stack pop problems. How should we analyze this smaller problem? You shall find that the first time the stack is emptied, if we have already counted the k elements leaving the stacks, this means that to the first element 1 to enter, we can give the label k to element 1. So if we ignore the element that is labeled 1, then before this element, k minus 1 elements must have been pushed in and popped. Then another problem remains. For example, right now outside the stack, how many elements have yet to enter the stack? Well, their labels will be k plus 1 to m. So there should be n minus k elements. So now we have analyzed the situation for an element labeled k. The first time the stack is empty, we have processed and push and pop of k elements. So now the problem has been split into 2 parts. If we ignore the first elements, we shall find that for the first part, we actually processed the k minus 1 elements. Well, for the second part, we processed exactly n minus k elements. So now we can use Fn to denote how many ways there are of popping elements in the stacks. For a set k, Fn is equal to Fk minus 1 multiplied by Fk minus k for different value of k from 1 to m. We can write out the equation for Fn, that is Fn equals F0 multiplied by Fn subtract 1 plus F1 multiplied by Fn subtract 2 and so forth, until the last term Fn subtract 1 times F0. Now we have a recurrence relation for existing the stack. Just now we'll analyze the stack. In fact, in terms of data structures, there is something else that corresponds to it. Let's have a look. This is a binary tree. So we can analyze the binary tree formed by n nodes. How many different variations are there? For this question, we can also use a distributed approach for the recursions. For example, for a tree like this one, we can use its root node for the partition. For the root node to separate a tree into its left side and the right side, how many nodes should there be on the left and how many on the right to separate the binary tree into its left and the right parts? We can find the recurrence relation by using the multiplication principle. So if we use T to represent, say Tij is used to represent the partition from the root node, there will be I child node on the left and a J child node on the right. So corresponding to it, the way in which trees are configured is simply T0 and -1, T1 and -2, and so on. So if for each configuration, if we let Fn be the number of possible configurations for binary tree containing n nodes, then we see a natural recurrence relation for Fn, which equals to F0 multiplied by Fn-1 plus F1 multiplied by Fn-2. We continue adding until we get Fn-1 times F0. This equation is precisely the same as the one we derived from the stack argument. Therefore, after with recurrence relation, we can set its initial value, assume F0 equal 1, and we can calculate F1, F2, and F3. So with this recurrence relation, we discovered that this is very useful in the world of computing. The numbers represented by this relation are known as Catalan numbers. Of course, Catalan wasn't the first to suggest this number. Back in 1751, Euler investigated this problem. You know, Euler usually corresponded with other mathematicians. Particularly well known is his correspondence with Goldbach over many years. The famous Goldbach conjecture, for example, were mentioned in these letters. Apart from the Goldbach conjecture, Euler also wrote to Goldbach, stating that he wanted to study how many ways there of dividing an n-gon into distinct non-overlapping triangles. For this problem, if we observe carefully, if we take a regular pentagon as an example, we can simply join up the different diagonals to obtain all the different triangles. How many are there in total? In fact, at that time, Euler gave a solution in the form of very complex equation. However, can we come up with an equation in recursive form? Let's match this up with an n-gon, naming the first vertex V1. Then the final vertex will be Vn. So we can simply take the side V1 with n to find the corresponding triangle. The other vertex of this triangle we represent by Vk. So this k can take any value from 1 to n. According to the value Vk takes, we can construct a fitting recurrence relation. Cn is equal to C0 times Cn-1 and so forth. So we would find that Euler did not obtain a recurrence relation. In 1758, however, another mathematician, Segner, proposed a recurrence relation which perfectly matched the stack and the binary tree problem perfectly. But as time passed, people only knew of the recurrence relation until 1838, when a new wave of research emerged. Multiple scientists delved deeply into this research, including, of course, the Belgian mathematician Catalan. At that time, Catalan was investigating the towers of Hanoi when he suddenly found its secret. He also conducted research into the representation containing brackets, etc. Naturally, there were many other mathematicians studying similar problems. But why is this sequence now known as a Catalan sequence? This was because in the 1900s, in a famous treatise, this work was attributed to Catalan. So everyone, when you write our papers, proper citation is very important. But who was the first to study Catalan numbers? Not Catalan, and not Euler. In two studies in 1988 and 1999 of mathematical literatures, we discovered that the first person to really study Catalan numbers was a mathematician from Mongolia. It was in the Qing dynasty in China that there was this Mongolian mathematician who studied the Catalan numbers before Catalan. In a treatise dating back to the 1730s, he details the construction of the Catalan number. In the modern age, the Catalan numbers has become an integral part of sequences. It was listed as a 108th in OEIS. We can see that the first few terms are 1, 2, 5, 14, and 42, and so on. Its growth is very fast. So, how should we calculate Catalan numbers? Of course, with such a recurrence relation, one might just think there some other ways to express it directly. This recurrence relation is somewhat different from the recurrence relation we have seen previously. Why? Most of the recurrence relation we have seen so far simply involved a linear summation. But for the Catalan numbers, we can see that its expression involves the multiplication of terms. So they do not conform to the linear summation relationship. We need a new method to express Catalan numbers directly.